Okay, so we're continuing in the asynchronous portion now, talking about these ligand receptor interactions or drug receptor interactions. We're talking about cation pi interactions, which this is a nice simple example of the idea. A ammonium species reacting with or interacting with a tryptophan indole heterocycle. This is a ADHD drug, kind of like an amphetamine style compound, maybe similar to like Adderall or something like that. But anyway, so as we were saying, there's kind of two situations where you find this interaction commonly. One is a drug-protein interaction. So like a drug binding to a protein or a receptor. And also it's found just in protein structure. So when, to keep the tertiary structure elements and secondary structure kind of together by having amino acids interacting with other amino acids and form like a reversible interaction, right? It's not covalent, it's a non-covalent interaction. So what are the amino acids that do this? These are a couple references. Dougherty is pretty well known in this field. This Chem Reviews paper is a pretty detailed review of all sorts of examples of cation pi interactions. Wikipedia actually has a nice overview also. It's a pretty simple summary of examples of this. So what are the amino acids? Usually it's going to be tryptophan or tyrosine as the aromatic amino acid, and then something with a positive charge. Arginine is a common one, nitrogen-based amino acid, which has a positive charge, and lysine also does this, but maybe it's found less often. Okay, so why does it occur? So if you think about a benzene ring, or a heterocycle, aromatic molecule, there's pi electron cloud above and below that essentially creates a partial negative charge. It's not a full negative charge, but it's like a delta negative type thing because there's a lot of electrons and electrons are negative. So you can kind of see that in this depiction with sort of a partial negative charge existing above and below, and then kind of a partial positive charge sort of on the outside. So there's most molecules have some kind of distribution of positive and negative charges. So how would substituents potentially change this interaction? Like something on the benzene. Think about that a little bit. Like what might, if I had attached something, if I had like a X group on here that that increased, or like we'll say donate electrons in. It donated electrons into the benzene. Would that make this a more substantial chart or more substantial interaction or less substantial? And if you think if a donating group is going to donate electrons in, it's probably going to make the interaction a little more strengthened, right? Alternatively, if you have something that's an X group, some random X group that's pulling electrons away, that's going to make less of a negative charge, and that would maybe decrease the interaction, and that totally makes sense, right? So this is an actual result, experimental result, looking at the binding energy of different benzene derivatives with sodium, which is kind of weird. Even sodium can participate in this. Na+, a plus charged inorganic ion. And just like we were saying, something that's pulling electrons away, like a nitrile, the C triple bond N is pulling electrons towards the nitrogen. Nitrogen's very delta negative. The carbon's delta positive, so that is essentially sucking electrons away from the benzene. And in this measurement, larger numbers are like a stronger binding, and so the nitrile has a kind of smaller number. Fluorine is also very electronegative. It's got a nice delta negative on it, and it's pulling electrons onto the fluorine. It also has a kind of decreased number when we compare it to like benzene. Benzene's unsubstituted. And then if we go the other way with a nitrogen, with a lone pair, a nitrogen lone pair that can kick in and donate electron density to the benzene, it actually has the higher number. Okay. So this just kind of shows it colorimetrically. And this is one of Dougherty's papers that kind of explored this interaction and characterized it a bit. Yeah, and as we were just mentioning, heterocycles like the indole and tryptophan also do this in addition to just benzene. And you can use these things called electron density maps. You may have seen them in organic chemistry as a way to kind of see, computationally predict how much electron density is present in a benzene or aromatic. And red is usually always electron rich. Blue is electron deficient. So let's look at a couple heterocycles like indole. You can see that indole has a lot of red in the aromatic ring system, suggesting a lot of electron density. And so it's very efficient at these cation pi interactions. Benzene does also, maybe not as much. And then oddly, pyridine, it's a aromatic heterocycle. It has very little of this. Now, of course, pyridine is not found in natural amino acids. So in terms of protein structure, we don't really see this present. But it's interesting to know that some heterocycles like pyridine don't really have this effect. You can also kind of, and there's also a red spot, which is the nitrogen. Nitrogen is a little more electron rich due to the lone pair, right? And we can also see, if we look at the right side ring of indole, it's a little bit on this orange side also. So it's a little different. And the part of the reason is that this nitrogen is donating us electrons into the ring, so it actually can, through resonance, you can draw the lone pair kick in and the double bonds shift around and basically be delocalized all over the ring system. This nitrogen can't really do that. Okay. And yeah, so this is red. This is actually blue because the nitrogen kind of gives up its electrons, right? Okay, and so that kind of shows the good, medium, and bad for this interaction. Okay, so let's look at a couple of these interactions in just protein structure. They are found in various proteins. So it's kind of cool to see them. And its purpose, I guess you could say, its role in protein structure is to stabilize the structure and maybe stabilize this alpha helix. So this is the cation pi interaction in Vaccinia virus protein VP39. Not exactly sure what this protein does, but it's an interesting example of this feature. There's a lot of interesting proteins with random tidbits and that improve structure. Okay, so this is visualized in PyMol, and it contributes to stabilization of the alpha helices. Another one is glucoamylase. This one's a little bit famous for having multiple interactions of the same type. So lysine 108 is the positively charged ammonium amino acid, and it's kind of surrounded by 4 aromatic ring systems that are all contributing to this interaction: tryptophan 120, tryptophan 52, tyrosine 50, and tyrosine 116. And this all kind of stabilizes the structure by all of these things being kind of attracted to that positive charge. And yeah, so this is a kind of an unusual example with a lot of these interactions, 4 of them. So this is the ligand-gated ion channel that we talked about earlier as an example of a ligand-gated ion channel. The nicotinic cholinergic receptor. Nicotine binds to this, and then that causes transport of the sodium into the cell, potassium out of the cell. And anyway, nicotine actually kind of binds through this sort of interaction, which makes it kind of interesting. So how does it do that? This is an example of, this is what the nicotine looks like. It's the sort of light blue colored species here. And it has a tertiary amine and a pyridine. And pyridines are not as basic as a normal amine. So which one of these is more likely to be charged as an like a ammonium with a NH plus? So the normal amines actually are more basic. If you you can see this with the pKa's. For the pKa's, you have to assume the protonated forms, and then look at the pKa's. And I think this one is about 9 if you protonate it, so with the NH. And I think this one, as the NH, is about maybe 5 or so. And so definitely an amine is much more basic, so it's much more likely to be protonated. Anyway, where is that in the structure? It's right there, and it is expected to have a positive charge as an amine and a proton. The proton isn't shown in the crystal structure because none of these protons are shown, but that is all. Amines are always protonated in physiological pH. So this thing is positively charged, and what's this? A tryptophan, 149. So this is right in the sort of position to effectively help bind this ligand. Okay. There's also these tyrosines up here that they may contribute. I think this one's a little better positioned, the tryptophan. Interestingly, the natural ligand of this cholinergic receptor, is acetylcholine, right? And acetylcholine has a positive charge, so it is. I don't have a structure of acetylcholine bound to the same site, but as a positively charged thing, it could potentially make interactions with all these things. It's just interesting that there's a lot of aromatic residues in the same spot that happen to have a positively charged ligand. Okay. Okay, another type of drug-receptor interaction. This one's a kind of weird one, and I actually only learned about this maybe about 5 years ago. It wasn't something I learned about in grad school, and it's very interesting, and it's kind of it's unique. It's called halogen bonding. What does that kind of sound like? Maybe kind of like hydrogen bonding, right? But it's weird because we usually think of halogens as a delta negative thing, right? And we think of protons as a delta positive thing, or fully positive, right? And so halogens appear partially positive and kind of acting like a proton, and it's kind of similar to the concept of hydrogen bonding. So halogens can almost act as like protons, which is totally weird. And how does that happen? And the concept is called halogen bonding. All right. So if we think about a normal carbon-based molecule and a halogen, you usually think of a bunch of delta negative all around, right? A bunch of delta negative all around the halogen, and that contributes to reactivity like SN2 reactions, where like a nucleophile can go attack the back and kick off the leaving group, like SN2 reaction, stuff like that. But if you consider the detailed structure of this, and this is kind of a new thing, it turns out that there's a little spot right here on the tip almost, and there's an angle of this. There's an angle of this that actually has a delta positive charge. And that is also electrophilic. And this is what we call the halogen bond donor site, which is kind of like a hydrogen bond donor site, right? Like an H+. That's kind of weird, right? Okay, and what else about this? Oh yeah. When we say nucleophilic over here, nucleophilic, like this area is nucleophilic. What do we mean by that? Remember, in organic chemistry, there are cases where the lone pairs can go attack stuff. Maybe not very commonly, but maybe a metal like aluminum trichloride, right? Aluminum trichloride or iron trichloride. The lone pairs are actually a little bit nucleophilic. So the lone pairs can actually attack stuff. Not usually in normal organic chemistry, but if you look at like the Friedel-Crafts reaction and aromatic chapter of the book, we have cases where the halogen lone pairs go attack stuff like a metal. Anyway, so this tip area is actually electrophilic, so things can either react with it or just like interact with it, and it's what we call the halogen bond donor site. This kind of shows what the predicted structure looks like for bromomethane. So there's kind of like a sphere with delta negative electron density kind of on the sort of inner part of this, but around the tip area it's considered more delta positive. Totally weird, something you may not have seen before. And this has been characterized. A couple reviews on this. The chemical reviews are always really good papers. JMedChem, deals with medicinal chemistry. This is a very important thing in medicinal chemistry because a lot of drugs use hydrogen or halogen bonding in their binding interactions. All right. The Wikipedia page is actually pretty good too. It's kind of a big Wikipedia page. If you want to read about this specifically for drugs, there's a section called the biological macromolecule section. A little condensed summary of halogen bonding for drugs. Okay, so the electrons sort of form a ring around the Br, and there's this thing called an electron hole, kind of at the surface, where it's sort of is delta positive, right around the surface in the tip. Okay, most profoundly at 180 degrees, but as you go up towards to about 130 degrees, there's still this delta positive little hole thing. All right, so it's a range. It's not just specifically 180. The strength of the interactions, if you consider like a proton, iodine has the most interaction, so that's iodine and proton are roughly about the same. And then goes bromine, chlorine, and then fluorine has very little of this interaction. So a big surface area, a large surface area like iodine or bromine is more likely to have this. Okay. Okay, let's look at a specific example now. So this is a nice characterized ligand that definitely, well, people think experiences halogen bonding, and there's some evidence to show that. It has a aromatic or heteroaromatic bromide kind of talking to a tyrosine, and is bound to this phosphodiesterase 5 enzyme. And basically, they made a series of inhibitors, fluorine, chlorine, bromine, and iodine, and then they looked at it computationally and also, I think, with X-ray crystallography, and looked at the IC50 values of this, and to basically see what sort of trend there is between the different halogens as they were building this model. And IC50 correlates with the calculated strength of the halogen bonds, and they were able to, based on the structure of the halogens and this predicted delta positive thing, they basically were able to predict a bond strength, and the IC50 follows that very nicely. Okay, and so here's that same example with the bromide and the tyrosine hydroxy group. And if they created this table that sort of shows this. On the left, you can see the different X groups, which are where the bromine is. And then they predict the bond angle. I think the determined bond angle was through crystallography. And generally speaking, the predictions and the determined are pretty similar. And also the angle between the carbon, the halogen, and the oxygen is kind of ranges, around 130, maybe upward, not as high as 180 for these. And they calculated the delta, the energy, I think, computationally, basically showing that, like we were saying, that iodine is going to be the best in this series, and then a little worse is bromine, chlorine, fluorine, and hydrogen, and that mapped very nicely to the IC50 value. And the best one of these is iodine. Okay, so hydrogen was actually in this case kind of bad. Well, it's actually not as bad as fluorine, which actually was a little bit worse. And then chlorine and bromine were maybe a little better, but iodine was definitely the best of these. Okay. This is an X-ray crystal structure that with the iodide actually, and showing the the bond distance and a very nice interaction between the iodine and the oxygen. One sec. Okay, let's see what else. This is another molecule with a bromide, and it is interacting with a threonine, OH. So there's also a proton on here that's not being shown, and this is also considered an example of halogen bonding. Okay. So there's various examples of this in the literature, and it's pretty well considered interaction. Whether or not they made an iodide version of this, that would be kind of interesting. At some point, the iodides would get a little larger and maybe bump into things, and that could be a problem. So usually the way you do this is you just make a series of compounds and then look at the IC50 and pick the best one. This is a aldehyde reductase inhibitor. It's another one. This is in interaction with acetylcholine binding protein and an aryl bromide inhibitor. So this also has the same kind of thing. It's a very simple molecule with a bromine on it, and that it makes that same kind of interaction. About 3.2 angstroms, kind of like a hydrogen bond. Talking to the leucine, acetyl bond O. So the halogen bond is acting like a delta positive sort of donor, like a proton almost, and the leucine is acetyl bond O is delta negative, and it's kind of talking to the bromide. Okay. Okay, so I want to talk about a website called Proteopedia real quick, which is pretty cool. Just some other place to look at things related to structural biology, and structural biology would be like crystal structures, and like other three-dimensional structures, NMR structures of proteins. It's nice that you can find X-ray crystal structures that have a specific property, maybe something like halogen bonding or cation pi interactions and things like that, or a protein that's involved in a disease. Kind of like a Wikipedia type thing, but for X-ray crystal structures specifically. So you can look for specific X-ray crystal structures that have a certain property. You could try Google searching these things. Proteopedia, table of contents, which shows the various topics, diseases, and types of protein structures. Proteopedia, cation pi interaction, to find proteins that have cation pi interactions. Proteopedia, halogen bond, and that'll give you more examples of halogen bonding. You can also, these will provide PDB codes that you're able to view within Proteopedia, or you can view them using this IC&3D thing that you guys have been using, or Pimal, or other tools like Chimera. Okay, so let's talk about dose-response relationships. We've seen this a little bit before. Let's go through one more time as we kind of finish this discussion of pharmacology. So when you think about receptors that are either occupied by a drug or not, the amount of receptors occupied is a function of drug concentration. So if you have a lot of drug, more of the receptors are occupied, right? As the drug concentration is increased, more of the receptors will become occupied until the drug basically occupies all of them, right? So this shows the two kind of types of curves that you might use for this. Either a linear curve where you measure percent of biological effect on the y-axis, and then a linear measure of the drug. And that gives you a pretty kind of not useful line, right? It's hard to actually see the IC50. It's really squished into this little range. So the better thing to do is really do a large distribution of drug concentrations, and then make this sort of logarithmic, or what they call semi-log scale curve. So we do x-axis on the logarithmically, and then the y-axis remains linear. And by making one axis logarithmic and the other not, is called semi-log, as opposed to making both of them logarithmic. That would be a fully logarithmic scale. That's what we mean. Usually semi-log are used in drug discovery to show dose response. Okay, so what are these words, agonist and antagonist, that we've seen before? There's kind of two categories, agonists and antagonists. Agonists are drugs that bind and activate receptors. You know that by now. Antagonists bind without activating them, and they consequently prevent binding of other agonists. So that's a way to kind of shut down a receptor or shut down a response. If you think of like a drug-receptor interaction as like a lock and key model, then agonists are the keys that fit and open and activate them, activate a lock or open the lock. Antagonists sort of jam the mechanism. That's a nice analogy. This sort of shows it graphically. So agonists occupy a receptor and activate it, so it sort of binds and activates it, right? If you mix an agonist and an antagonist, it's sort of, it still gets activated, but it's less so. A full antagonist response will just completely shut down the receptor and the response. Okay, so when we consider agonists, we need to consider a couple factors about them. Potency, of course, is the amount of drug to produce the effect. of a given intensity. And we can measure potency with EC50, or if it's an inhibitor, often we use IC50. Efficacy is the ability of the drug to produce a maximum response, like a fully effective dose. And that's kind of a general term. We'll see examples of this. And we look at, when we consider efficacy, if two drugs both shut down a target completely or cause a maximum response, they have the same efficacy. But some drugs will have more efficacy, some drugs will have less efficacy. And then there's partial agonists, which produce less than a full response, like maybe 50% response, even if they're completely like a high concentration. It's not like you'll necessarily reach 100% response. Okay, and one sec. All right, so let's look at a couple of these kind of general examples. Agonists with different potencies. So that's pretty easy to imagine. We have different drugs, A, B, C, and D, and they all are different potency. And they could all be related drugs. Maybe one has a chlorine, and one has a bromine, one has an iodine. Those kind of examples. We've seen these also in some of the recent homework assignments of different drugs with different potencies, right? And they all would usually have this same kind of curve. So, which is the most potent drug of these? The one with the lowest IC50 or EC50, which would be A. So at lowest concentration, it has the highest. Lowest concentration, it has the reaches the maximal effect earlier at the 50% response at the lowest concentration. Yeah. Okay, so then we have partial agonists, A, B, C, and D. Whoops. Let's look at these examples. So they all have the same EC50, but compound A has the highest efficacy, B is a little lower, C is lower than that, and D is lower than that. So in the real world, we actually have both of these situations, and some drugs just don't reach a full efficacy of 100%. All right, so we've talked about IC50 and EC50 before. Let's give a formal definition of IC50. EC50 is the same thing, except it really refers to efficacy. IC50 refers to inhibition. Okay, so this is the Wikipedia definition. That's actually pretty good. The half maximal inhibitory concentration, IC50, is a measure of the potency of a substance in inhibiting a specific biological or biochemical function. IC50 is a quantitative measure that indicates how much of a particular inhibitory substance, like a drug, is needed to inhibit in vitro, but it can also be like in a cell-based model or something, a given biological process or biological component by 50%. So it's not giving you the 100% inhibition, but it's still a good, general measure of potency. And this just shows that kind of example of, if we assume full response of full activity of a enzyme or something at low concentration, that if you start titrating in more and more drug, eventually it drops off and you find the IC50 value. This one's about 320 nanomolar. And then as you keep going, eventually it completely drops off. Antagonists are drugs that bind to receptors with good affinity, but they do not stimulate the receptor, and we call that kind of low efficacy. It's a little counterintuitive, because if it is a good antagonist, you might still consider it efficacious. That's kind of just a definition question, or a semantic difference, I guess. But antagonists produce low efficacy in terms of we're blocking a biological response, right? Okay, so then lastly, or moving to the end of this, let's talk about competitive versus non-competitive antagonists and see what the differences are between those. So, kind of from the name, you can imagine what a competitive antagonist might mean. It binds reversibly to the same receptor site as an agonist, but since they bind reversibly and they kind of compete for the same binding site, they compete with each other, and you can surmount the effect of the antagonist by adding more concentrations of the agonist, right? So if I have the antagonist bound and I start adding more and more agonist, eventually the antagonist won't have as much effect. And this contrasts from a non-competitive antagonist, which may bind irreversibly through covalent bonding. Where have we seen that before? That, like the concept of suicide substrates, like clavulanic acid and antibiotic research. So they might bind irreversibly to the same site, and it reduces the binding of the agonist permanently and through a covalent bond. The primary effect of a non-competitive antagonist is reduction of the maximal effect. So that'll actually decrease the maximum response. So you can't reach 100% response anymore with an agonist. Let's show some examples. All right, so isoproterenol is a beta adrenoreceptor agonist, right? It's kind of the opposite of a beta blocker. Beta blockers are beta adrenergic antagonists. So what this does is it increases heart rate. It's used to treat basically slow heart rate. So if you have a slow heart rate, you can receive this drug and it'll increase your heart rate. Okay? It's an agonist. And propranolol is a beta adrenoreceptor antagonist. It's a beta blocker. Okay? It's used to treat hypertension and high blood pressure. So if you have, hypertension or anxiety and things like that, you may be prescribed propranolol. Okay, so these both bind to the same receptor. Interestingly, the structures are very similar too. They both have the alcohol and the isopropylamine, but the agonist has this sort of catechol benzene with the 2 hydroxy groups, and this has like a naphthalene. That's kind of that little difference is the difference between being an agonist and an antagonist, right? Okay, so if we just if we consider on the x or the y-axis percent increase in heart rate, and we just add isoproterenol, we get an EC50 of a little bit under a maybe 0.9 nanomole or something, around 1 micromolar. Okay, and then we have a maximal response eventually at a higher concentration. But if you provide a mixture of the agonist and the antagonist simultaneously, the main thing, as you might expect, is these are going to compete for the same binding site, and as we add more, well, if we have this combination, then by adding isoproterenol, now the EC50 increases. So you have to actually have more because they're competing for the same binding site. And if you add the same experiment, but you add 2 times the amount of the antagonist, propranolol, then the EC50 is even higher. But nevertheless, with a competitive antagonist like this, you still max out at 100% increase in heart rate. It's just you would need more of the agonist. Okay, hopefully that makes sense. Nice example of a competitive antagonist. So conclusion, propranolol is a competitive antagonist of the beta-adrenoreceptor. It reversibly binds to the same receptor in competition with the agonist, which is isoproterenol. Now, what about these non-competitive antagonists? So these are ones where maybe there's a covalent binding event or something that is blocking binding to the receptor or something like that. So let's consider norepinephrine. It's a neurotransmitter that binds to the alpha and beta adrenoreceptors. It increases heart rate, blood pressure, fight or flight response. It's an agonist of the adrenoreceptor. And then let's consider this this drug, phenoxybenzamine. It's a beta or alpha adrenoreceptor antagonist, alpha blocker. It's also used as an antihypertensive drug. Okay, interestingly, it has this halogen in there, and that's going to maybe, what type of chemical properties do alkyl halides have? It may be an electrophile. It could potentially be a mechanism where the protein actually gets attached there, and that's probably what's going to happen. All right, so, but this is going to be considered a non-competitive antagonist as opposed to a competitive antagonist. And how's this going to work? All right, so first, if we just add norepinephrine and we measure percent increase in blood pressure on the y-axis, and we titrate in norepinephrine, it achieves 100% response at a certain EC50. Okay. And if we add norepinephrine plus some of this non-competitive antagonist, we actually have the same EC50, but it basically maxes out at a different level, because when this stuff binds, as you'll see, it binds covalently, and when it does that, it's basically permanently blocking those receptors, and so it's just impossible to achieve the 100% increase anymore. And if you add 2 times this molecule, then you even have a lower maximal response. But notice how the EC50 of norepinephrine is all the same. It's just that's kind of the difference between how you know the difference between a non-competitive antagonist versus a competitive antagonist. Conclusion, phenoxybenzamine is a non-competitive antagonist of adrenergic response, covalently attaches to the receptor and permanently, irreversibly inactivates it. How does it actually do that? That's a really cool question. As an organic chemist, I love these kind of questions. But it probably has to do something with that chloride, right? Okay, so this is just a summary of those two real quick. Competitive inhibition, again, isoproterenol has different EC50 values based on the amount of propranolol added. So isoproterenol is an agonist that can be blocked competitively by an antagonist like propranolol. And so the maximum response, though, is not affected by a competitive antagonist, right? So propranolol is the competitive antagonist here. Okay. Right. Isoproterenol is the agonist. Okay, so norepinephrine has the same EC50 value regardless of the amount of phenoxybenzamine added, but the maximal response is achieved, that can be achieved, is diminished. Phenoxybenzamine is considered a non-competitive antagonist. Okay. So how exactly does phenoxybenzamine covalently attach to the alpha adrenergic receptor, making it a non-competitive antagonist? That's a good question. You could almost imagine that maybe the receptor just directly attacks the carbon and kicks off the chloride, but probably doesn't do that. It's an interesting mechanism. When you have the nitrogen nearby, the nitrogen is able to actually attack and kick it off and then make a different electrophilic intermediate. So what probably happens is cyclization of the amine to the terminal chloride to create an electrophilic aziridine functional group. It's kind of like an epoxide, and then that can be maybe attached to the receptor. So this is probably what's actually happening. Nitrogen attacks, kicks off the chlorine. This thing is a aziridine, is an electrophilic intermediate. The receptor, what is doing that? It's probably characterized, but it could be a lysine or a cysteine or something, some nucleophilic residue in the protein that attacks it. Now this thing's kind of attached. It's funny, this is a clinical drug, right? So it's actually used like as an anti-hypertensive drug. Clinically, I mean, like a clinical drug that's permanently attaching to your receptors, how does that even work? I mean, you're I mean, in a way, for some drug targets, that's okay, because for one, the receptors do recycle, and the proteins get degraded and resynthesized by your body. There's like garbage collection mechanisms. The other thing is, like, for hypertension, you're trying to really stop binding to that receptor, and as long as you're doing it in kind of small amounts, it's actually kind of an efficacious goal, I guess, right? But generally speaking, though, I think like permanently modifying your proteins isn't necessarily a good thing. Okay, so it's surprisingly similar to how mustard gas, which was used in like World War I, I think, was used as a chemical weapon. So it's a similar kind of idea. These weird molecules with the chlorine and the sulfur and the chlorine, it's called sulfur mustard. Historically, I forgot why they call it mustard. It's not the kind of mustard you eat. But the sulfur attacks, and you get this episulfide thing, which is another electrophilic intermediate, and then your biological molecules in your skin, lung, DNA get attached. And then this, especially in your lungs, because if this kind of happens in your lungs, there's a lot of biological problems: blistering, swelling, burns, cancer later in life because your DNA gets alkylated. So why doesn't this happen up here? What's the difference in the structure? Probably something about the phenoxy group that's maybe causing selective binding to the adrenoreceptor or something like that. So if this drug had non-selective effects and attached to your lungs and things like that, that would be bad, and it wouldn't be used as a clinical drug. That's my guess. This kind of really simple molecule, these sulfur mustards, do not. They just bind non-selectively to everything they see. I think I'm done for today. Am I done? Yeah, I'm done. We have a next section, and I think this now is probably the best place to stop. So I'm just going to keep going next time into a different topic. So we're a little shorter lecture today, but that's okay. All right. So have a great night, and I'll see you guys next week.